Okay, so from now on, I should wait for 20 seconds, right, or something like that.
Okay, have a good class. I will leave now. See you, Pierre-Louis.
Okay, merci. Ciao. Okay, can I start now, you think?
Maybe we can wait 1 more minute.
Okay, great. Okay, shall we start now?
Yes, I was waiting for Damian to enter, who was the one who asked for this modality. But yeah, he's in. Yeah, I think you can start.
Okay, so great. So this is the third day of these lectures. And I will first summarize rapidly what we have done yesterday and start today's lecture proper. So we reviewed induction principles for various types. We studied in more depth the use of path induction to show how to concatenate paths, to show how to turn functions into functors, to turn dependent functions to something like dependent functors, even if this notion is not is not a categorical notion. We defined the notion of transport, which was which is very, very important. And then we started to discuss the notion of equivalence, various notions of equivalence. First, the notion of a notion of equivalence in the function type A arrow B, which I called homotopy. And then later I explained an axiom which says that this notion, so which is recorded here. Okay, so by definition, the F being homotopy to G is that for all X, you have a proof that Fx is equal to Gx. And then later I told you that there is an axiom that we add to our type theory, which says that two functions are equal in the propositional sense if and only if they are homotopic. So this is a description. Thanks to this axiom, we have a concrete description of what the equality of functions is. Okay, and then I started to discuss the notion of equivalence between types, which will later lead also to another axiom, which will make clear how we can prove that two types are equal propositionally, namely through the univalence axiom. And I started to discuss at least two different ways to say that two types are equivalent. First, through this this type here, which I call Q-inv. And this type says that F has a right and that that with F is associated a function that goes the other way around, and that happens to be the inverse up to homotopy of F. So you see that the same G here is witnessed here as being left and right inverse of F with respect to this notion of equality of functions. Okay, and then a little bit later, so I discussed some properties of transport. A little bit later, some properties of homotopy, and a little bit later, I introduced this other seemingly very close way, very similar way to state that F has an inverse, namely that it has. So it's another type, okay, which says that F has a left inverse and a right inverse, but doesn't specify that those are that it is exactly the same function. Okay, and then there was a discussion in my lecture and also on Discord on what does it mean that these two types that we described are logically equivalent and not, as I claimed, and I will eventually go a little bit more into that towards the end of the lecture, and probably I will start tomorrow to explain this exactly and in the best way I can. So the point is that I also explained the difference between logical equivalence and equivalence. Yes, here. Okay. So I introduced the notion of equivalence, which is the existence of a function that has a left and a right inverse. Okay, and then yes, and then I introduced a weaker notion, which I called logical equivalence, where you see the difference between Q-inv, which leads to this notion of being equivalent, and being logically equivalent. Okay, so logically here is important because it's weaker. It's just that when it comes to logical equivalence, the only thing I have to do is to exhibit a function from A to B and a function from B to A. And here I must say that I gave a wrong answer on Discord to someone who told me he told me something right, and I told him that it was not right, but it was right. So if you know that your types are inhabited, okay, so that you have at least one element in capital A and at least one element in capital B, then of course you can find a function from A to B, because you can take the constant function that maps all elements of A to this chosen element, chosen inhabitant of B, and the same in the other way. So it's a way to say that being logically equivalent is a very weak notion, because somehow, well, by just what I said, as soon as A and B are both inhabited, then they are logically equivalent by what I just said. So you see that, morally speaking, being logically equivalent is a very weak notion, and you cannot expect that it is the same as being equivalent, because being equivalent is much stronger, because you want these functions to be inverse of each other. And the logical equivalence doesn't require that. Okay, the second question is which was raised later on. It was when I showed this logical equivalence between QInv and ByInv. Some persons also on Discord asked, but okay, but why isn't this an equivalence? Okay, well, it's hard to prove that it is not an equivalence, and we will actually prove that it is not an equivalence in an indirect way by showing that this guy is a proposition and this guy is not a proposition. By the way, I will not show because the proof is a bit difficult, and I will lack time to show that this type is not a proposition. But you can refer. I will refer you to the hotbook for this part. So, but okay. So we will know indirectly that these types are not equivalent. But I want to size just this moment to tell you why it is not very clear why they should be equivalent. Well, what I did to prove the logical equivalence between them was to show how from the data, so how to define functions from here to here and functions from here to here. But if so, you see that a member, an inhabitant here or here consists of several data. It consists of here just one inverse, and here two inverses, the left one and the right one, plus some other components which are the proof that this holds and the proof that this holds, for example, for ByInv. And okay, so here let me give a name to such things. Okay, so for example, this will be called epsilon, and this will be called eta. So you see that if I start from here, if I start from here, I go there and I go back, then you see that I will have to, in order to show that the results are equal, I will have to show that the inverse component, because in both you have an inverse component, here just one and here two. Okay, you have to show equality between these things. This is not too bad, but you will have also to show the equalities between the epsilons and the eta. Okay, because here we have an, for example, here we have an epsilon and eta. We turn it into an epsilon prime and eta prime here, and we turn it into an epsilon second and an eta second here. And in particular, when going from here to here, we did a lot of work, which was written here. Okay, there was, well, it's elementary mathematics, but when it comes to write down exactly all the combinations of eta and epsilon that are involved, it's quite a lot. And then so we will have to prove that eta is equal to eta second and epsilon is equal to epsilon second. And you see that we need to care for equalities deeper in deeper in the structure. We are not looking only at the equality of functions, but we also need to look at the equality between equalities, because this is an equality. So you need so what we will end up is having problem with something called higher coherences, and unless I've given more information, I have no tool to deal with them properly. And this is an intuitive reason why this is not going to hold as an equivalence. Okay, I hope this helps a little bit to solve the puzzle that some of you have, and even beginning with me when I started to study these things. Okay, so what did I do otherwise? Well, I also characterized the equality on product type, on sigma types. And this was a motivation to say, well, if we can characterize the equality on sigma types in terms of smaller types, well, then we should also be able to do this for function types. And this is what leads to the extensionality, or we should be able also to say, to characterize the equality on the universe, and this is what leads to the univalence axiom. Okay, so let me repeat this axiom. So univalence, I will not repeat extensionality, but I will repeat univalence. So you have two decent notions of equality between types. The one provided by type theory, the propositional equality on the type U, okay, which is a type of all types, and this notion of equivalence of types, okay, taken to be with bi-inv, okay. And why bi-inv? Because we will see, maybe today we have time, we'll see that this is a well-behaved type in the sense that this is a proposition. We already learned about types being propositions at the end of last lecture. Okay, so this Q-inv is not, so we prefer to have a bi-inv here. Okay, and these are the two notions that we have, and because we have path induction, we know that we can define quite easily a map in this direction by path induction. Okay, this map is called id to ECV, and the axiom of univalence says that it has a left and right inverse. Okay, and here, well, here I can use really Q-inv. Where I cannot use Q-inv is when I encapsulate the information of being equivalent in a type. This is where it becomes dangerous. But when it remains at this level, to prove that two types are equivalent, because it's all about being able to prove it, then whatever logically equivalent way of proving it is okay. Okay, so this is why I insist on having two symbols. This symbol is a serious internal symbol that I can only use when I form a new type, which is this one, while this one is a bit more is higher in it's more meta theoretical, if you want. It is just to say that I have two functions that are quasi inverses one to the other. Okay, so yes. And then I started to discuss a first application of univalence, and this is where the lecture of today properly starts. So let me remind you what the theorem is about. Well, before the theorem, let me go through this slide again. So if you have two types x and y, if you have a function from x to y, then you can organize the material of this function in order to build a type family indexed over y. And the idea is that for each element, for each inhabitant of y, of capital Y, you can define a type which is called the homotopy fiber of S at Y. And it is this type. Well, if you read it set theoretically, it's a set of all x's that are mapped by F to Y. Okay, but homotopically, it's a much richer type because it's not a set. I mean, we are in type theory. So we have this notion of homotopy fiber, and since this is for varying small y, we have produced a family. Let me check. I don't have. Do you? Yes. I don't know what happens here. I'm not sure to have the. No, it's okay. It's okay. It's okay. I cannot see. I cannot see the participants. Yes. Okay. Sorry. I have the list of participants. Yes. So let me continue. So this was for the. This was for getting a family of types index over y given a function from x to y, and conversely, given a family of types p from y to u, so a family of types indexed by capital Y, I can collect all the information of p in a single type, which is sigma y p of y. So the inhabitants are a pair of an inhabitant of capital Y and an inhabitant of the type py. And this type is equipped with a function that goes to y, which is just the first projection. So you see that from a type family indexed by capital Y, I can get a function into y. Okay, so let me remind you what the statement is of this theorem, which we could call Grothendieck equivalence, because the construction is very much related to something called Grothendieck construction in category theory. The theorem is here. It says that the type of all type families indexed by capital Y is equivalent to the type, to this type here, which is this one, which is the type formed by a pair of a type and a function from this type to y. Okay, so this is our goal. And now we proceed to the proof of this goal. So the first, so we need some preliminary lemmas in order to prove this theorem. And the first one is it is this property dagger. Okay, so it says that for all type capital Y, for all type family indexed over capital Y, and for all element B of capital Y, we have an equivalence between PB, okay, which is a type, it's the instance of P at B, and the fiber of the projection function, which is here, at B. Okay, so what does it mean? What does it mean? So let's see what is a guy typically living here. So by definition of fibers, it consists of an element. Okay, PR1 is of this type. Okay, so you have an element here is a triple of this form. The first element in this triple is an element of this type. And the second element is a proof. Okay, yes, here we should replace in this notion of fiber, which is here. Okay, we should replace X by this type here. This is why I have a pair whose first element is a pair, because the first element should be here. But this here is instantiated as a sigma type. So here I have as first element of this pair, a pair. And this pair is an element of sigma y py. Hence, it is something of the form y, comma r. Okay, so y is an element of capital Y, and r is an element of py. Okay, so here there's a typo in my text. It's a py here, and the rest here is a proof that that the first projection of y, which is y, okay. So here it's a certain q, okay, and this q is a proof that PR1 of YR, which is y, is equal to R. Hence, this q here is of type y equals R. Okay, and what we want to show is that all these triples here reduce somehow homotopically to just elements of PB. Okay, so it's a kind of noisy way to speak about PB. Okay, so what is the idea here? Well, the idea is that, again, it's an idea of path induction. The idea is that why because okay, let's be very naive. Because y is equal to R, we could as well have started with R, okay, and then here we would have taken the reflexivity. Q would have been the reflexivity. So you see that, morally speaking, here all of these guys are a fattened copy of members of PB, okay, which is here, okay. Or if you prefer, an element here is not necessarily directly an element of PB, okay. It could be an element of some other member of the type family P, okay. So oh, sorry, what no, sorry, I take it back. I'm speaking about R, okay. This R here is a member of PY, okay. But what I'm meaning is that all what matters is the case when R is actually all what matters is when Y is actually B and R is an element of PB. If Y is not an element of PB, by definition of fiber, it is equal to R, okay? So, no, something, am I correct here in what I'm saying? No, I'm not correct. This is why I'm so confused. Here is Y equals B. I'm sorry. I'm sorry about that. Yes, because we are speaking about the fiber over B. Okay, so let me repeat. I'm losing time here because I confuse myself. So let me repeat. The fiber here is defined to be the set of pairs of an element of this type such that its first projection is equal to B. Okay, and what is the such a pair is of the form YR. Okay, the first projection is Y, so Q is a proof that Y is equal to B. Okay, and then what I say begins to make more sense, I hope. So the idea is that if Y coincides with B, okay, then this R is an element of PB. If Y is not B, it is still equal to B, and hence these elements of this component py, they are very much related to pb. Okay, so you can contract. The idea is you can contract the whole of this thing to pb. Okay, sorry for being slow this afternoon this afternoon for me. And let's proceed now to the proof, because my intuitions are a bit too confused at this particular moment. So let's do the proof rather than trying to guess why it holds. So we need to find two functions, one here and one here. Okay, so the first one takes an element here. So I'm first defining phi that goes this way. So I take an element R in PB, and I can associate with it the triple BR ref of B. Okay, so this is clearly satisfying the specification because R is in PB. Okay, so BR is in sigma y py. And then the first projection is B. Okay, and we want to prove that B equals B, and ref B is good. Okay, on the other way around, we need to define a function from here to here. Okay, so by induction on sigma types, because this is a sigma type, it's enough to specify psi when I give it explicit members of this type, and I have just spelled out to you what are these explicit elements. They are triples formed by a pair of y, r, and q, where y is in capital Y, r is in py, and q is a proof that y is equal to b. Okay, so this is what we need to specify. But you see here that everything is varying here, okay, except b. But we can do something called base path induction. As I told yesterday, it's not a problem to fix one endpoint, provided the other is variable. So in order to define this function, it's enough to do it when y is exactly b, and then when q is exactly the reflexivity. So it's enough to specify this function for BR, a ref of B. And then we set it to be equal, definitionally equal to R. So by path induction, base path induction, I have a function psi. Now we need to show that they are inverse. Okay, so if I start from R and I do psi of phi of R, then that is the easy case because phi of R is this guy, and precisely I have defined psi in such a way that I return R. So you see that this holds by definition. Hence, this is true for every R. So a fortiori, it's an a fortiori because this implies that they are equal. Definitionally equal implies equal, and hence you get this homotopy here. For the other direction, we have to show that phi of psi of any triple YRQ is equal to this triple YRQ. Okay, but again by base path induction, because here y and q are varying freely, it's enough to do it for the case BR ref B for exactly the same reason. So we have to check that phi of psi of BR ref B is equal to BR ref B. But this is easy because phi of psi, again, for the very same reasons, by the definition, if I take psi of this guy, this is R. If I take phi of R, this is this guy. So this guy here is definitionally equal to BR ref B. And we need to find a proof that phi of psi, etc., is equal to this guy. But I can replace, because it is definitionally equal, I can replace this guy by this guy, and then reflexivity on this guy will do the job. Okay, so this proves the lemma, and then we will see later on how to use it. Okay, so now let me remind you, I think I went through last time. So the theorem, I already recalled it, and let me remind you that we already defined the two functions going here and here. Okay, so the first one takes a family, so the psi goes this way. It takes a family and returns the total space here together with the projection, as we have seen, and the map in the other way. He takes a function, well, a pair of a type x and a function f from x to y. It takes it to the family phi(f), okay, which is a family of type because it's a family of all fibers over all elements of capital Y. Okay, so we can see easily that if we apply psi followed by phi, what we get, okay, psi takes me to this guy, and then I take the fiber for this map. So you see that by definition, I get phi of psi of p is phi PR1. Okay, but what did we just prove? We just proved that these two types are equivalent. Okay, so they are equal by univalence. I forgot to write it. I will correct it. So here we use univalence. These two types are equivalent, hence they are equal, and this is for all B, hence Fib of PR1 is equal to P. Okay, so let me repeat. Fib PR1 applied to every element gives equivalent types, hence equal types. So here I have equal, this is for all B, and this is exactly the definition of saying that Fib PR1 is homotopic to P. Okay, so you see that phi of psi of P, which is definitionally equal to this guy, is homotopic to P, which is what we want. So that's one direction. For the other direction, we will also use univalence, I guess. I think, yes, we also use univalence. So we will use univalence twice in this book. For the other direction, we need some preparatory material. So the preparatory material is that we need to discuss what it means for two inhabitants of this type here to be equal. So we want a characterization of the equality over this type, U over Y. And here it is, and we are going to prove it. So we can show that blah, 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 yes, to say, no, this is a preliminary property, so maybe I should go directly here. Yes, here is the characterization. So the characterization I'm seeking is this one. I want to show that two inhabitants of the type U over Y, namely some AF and some A prime F prime. So A together with S that goes from capital A to capital Y, and capital A prime together with a function that goes from capital A prime to Y. And the theorem tells me that they are equal propositionally if and only if I can show that there is an equivalence between A and A prime, and F can be obtained up to homotopy. So F is homotopic to F prime, but I have to adjust F prime with respect to F, because F is going from capital A to capital Y, while F prime is going from capital A prime to capital Y. So I need to compose F prime with a function that goes from A to A prime, but I have one, because E is a proof that A is equivalent to A prime. So it is a sigma. Remember that this type is sigma F dot by inv of F. Okay, so if I forget this component, if I take the first component of E, I get my F. And this F is a function from A to A prime. So PR1 of E has the right type, and this expression type checks. Okay, so my goal is to prove this theorem, but before I prove it, I need to prove some preliminary result, which is here. So this result is the following. Okay, so let me state it. Suppose that we have a proof that two types are equal. Suppose that we have a function from A to Y, a function from A prime to Y. Then you see that if I take the type family, which maps Z to Z arrow Y, I can transport relative to this type along the path that goes from A to A prime. I can transport F, and the result of this transportation is that F is this transport, it lives here. Okay, that's what the type this type family is doing for us. Okay, so this type checks again. These two guys are in the same type, and then what the property says is that the equality type between the two is equivalent to proving that F is homotopic to F prime composed with, and here it's essentially the same idea as the one here. I need to cook up a function that goes from A to A prime. And because I have this type equality here, I can transform it into a proof that A is equivalent to A prime through the id2xv function. And I can take its first projection, which yields a function from A to A prime. Okay, so this theorem, how can we prove it? By path induction. And this is easy, this doesn't require univalence. How do we do it? Again, because everything here is varying, so we can take P to be the reflexivity, but in case P is the reflexivity, then we know that transport does nothing, okay? So the transport of ref AF coincides with F, so this guy coincides with F, okay? So here we just have have F equals F prime, and here we know that e to x v of reflexivity consists only of identity functions. So the function part, which is PR1, is the identity function. So we know that this is definitionally the identity function. We know, of course, that composing with the identity function is doing nothing. So we know that this guy is F prime. So our problem here in the case where P is ref reduces to F equals F prime is equivalent to F homotopic to F prime. But this is a functional extensionality, extensionality, and since we assumed it, it holds, and we have proved this fact here. Good. Now let's prove this other fact here, which is very similar. Okay, except that here it was about equalities. Yes, P was varying here over the equality type, while here E is varying over the type of equivalences between A and A prime. That's the only difference. The only difference. Okay, so let's prove it slowly. We want to prove the equivalence between this type and this type. So let's start from this type. We know, because we already characterized no, we know because we already, sorry. Am I doing something? Ah, yes, so sorry. Yes, to prove this is because this is a sigma type here. Prove this is the same thing as giving a proof that A is equal to A prime, and proving that by transport, okay, transporting F is equal to F prime. So you have an equality between the result of transporting F and F prime. Okay. Now we just proved that this guy is equal to this guy. This is what we proved here. Okay, so by what we have just proved, we are here. And now it's just a matter of using univalence, because, well, the idea, well, let me be intuitive here. The idea of univalence is that, well, all the proofs that A is equal A prime are of the form UA of E. Remember that UA is the axiom that turns an equivalence into an equality. So here we could as well consider only the case where P is of the form UA of E. And you say that here, if we put UA of E here, we have E to XV of UA of E, but UA being an inverse to E to XV by axiom, this is just E, okay, up to equality, okay. But here we all deal with things up to equality because it's homotopy here. So you see that you turn this type into this type, okay, by an equivalence, and this is by univalence. And this is what is stated here. Okay, so we have this nice characterization of the equality over the type U over Y. Okay, so to summarize it in more concrete terms, if we want to prove an equality in U over Y between AF and A prime F prime, what we need to do is to find a function from A to A prime, a proof that epsilon, this function epsilon is bi-invertible, and a proof that F is homotopic to F prime composed with epsilon. Okay, good. So now we have to remember that we had shown, yes, so we had these two inverse functions psi and phi, and we were missing 1/2 of the proof that they are inverse. Namely, we were missing the fact that phi of psi of xf is equal to xf. Okay. So this is our goal. So, but let us first see what is psi of xf. Well, if you remember, phi of xf returns a fiber, okay, and then you take PR1 over this family. Well, here you have this type, total type, and PR1. So if you put this together, you see that psi of xf is this type here. Okay. Electricity here. Okay, so what we want to show is that xf is equal to this new type here. Okay, so according to what we just showed, we need to find, what do we need? We need a function from this type to this type. We need this function epsilon. We need a proof that it is bi-invertible, and we need a proof that PR1 composed with epsilon is F. Okay, so the function is easy to define. We start from X, which is an element of capital X, and we look for an element of Y, first of all. Why? Because F is a function from X to Y. I can take F of X. Yes, maybe I should recall here that this F here is going from X to Y. So F of X is a good element. And then an element in the fiber is easy because we want to prove that we want a proof. No, we want an element in this fiber, and one element in the fiber for F of X. So here we look for an element for fib F of Fx. Okay, so we look for elements. Let me call them X prime, such that F of X prime is equal to F of X. But there is one in particular, which is X itself, and then I take ref of F of X. So this checks properly. Okay, so this is a member of the fiber at F of X, and this function is defined properly. Then by definition, you see that if I do epsilon and then the first projection, what I get is F of X. Hence, I get this for free, that the pre-R1 composed with epsilon is equal to F, even definitionally, so a fortiori homotopic to F. So now we need to prove that this guy is inhabited, okay? But it's as well, I can prove that this guy is inhabited, because then by logical implication, this guy will also be inhabited. Okay, so we need to find an inverse. We need to find a function that goes from here to here. Okay, and this function again is quite easy. So you take an element in this fiber, and you can take it to be triple, because again you do induction on sigma types. So you can take it to be the pair of an element of capital Y and an element of fib F of Y, which is typically some XR, and this X is in capital X. So you do the projection on the second component here. And we have to prove that alpha and epsilon are inverses. Okay, so alpha of epsilon of X, it's easy because what? Because if I do epsilon of X, I get this thing, and if I project on the thing on the middle, it's X. So this holds without any difficulty. And for the converse direction, we have to prove Okay, again, using induction on sigma types, we have to prove that starting from EYXR, sorry, yes, and doing the epsilon and then the alpha of YXR, I find two equal terms. Okay, so let me see, let us see. So alpha of YXR by definition is X. Epsilon of X is F of X, X ref X. Okay, so what I have to prove is this thing here. Okay, but again here we can do path induction. Why? Because my R here, so I can leave X fixed. X is fixed. F of X is fixed. Okay, and we have maybe to remember what is the type of R. So the type of R here is, if I'm correct, is the proof that f of X is equal to Y. Yes, it's yes, because it has to be in the fiber of Y. Yes, so you see that if X is fixed, then f of X is fixed. Okay, so this guy here is fixed, but this Y varies and this R varies, and we are in the situation of based path induction. So this Y varies, and we can take it to coincide with Fx, and we can take R to be the reflexivity. So we need to check this only in the case where R is reflexivity and Y is f of X. But it is exactly what is written here. So in this case, we have this holds by reflexivity. Hence, it holds for all YXR. This is again the magic of path induction. So I think this concludes the proof of the Grothendieck equivalence, and I like this. So I don't think it's it's in the hot book, and I took it from Hugo Monclay's notes, and it's one of the simple, cute results that uses univalence in a nice way. Okay, so let's move on and continue the discussion that I started at the end of last lecture. I started to discuss the notion of proposition and the notion of contractible type. And I might also have discussed the notion of set, but I'm not sure. Anyway, I will go slowly for. Okay, so proposition. A type is called a proposition if you can find an inhabitant in the following type, which says that for all x, y in A, X is equal to Y. Okay, and yes?
Sorry, excuse me, there is a...
Damian, yes. So can you, yes? Can you just ask?
Hi.
Hi.
Good to talk with you. No, I had a question like in the intermediate space after you started with this. Maybe I can do the question because it's a little bit out of the diapos right now.
Yes.
And maybe you can choose to answer it later. I have no problem with that.
Okay.
So I think path induction is really powerful. But it's, and of course, if you have a generic type, you can't assume anything about the structure of the path, the path in there. But my question is, when this if this happens to need to be defined at some point, like the group structure of the pi1, let's say.
Yes.
So So of course, if you talk about the generic space, you will only have the null group. But when is the point that you need to define non-trivial, something analogous to non-trivial groups on there?
Okay, I'm not sure to understand exactly the question. Yes, when we will come to circles, okay, on things like that, and compute the pi1, because this is also on my stack of things to do, we will meet a type in which you have a non-trivial path, which is a loop, okay, and it's a bit confusing to think that you still will be able to do path induction in this setting, and the answer is yes. You don't need to be confused because this path is highly this special path that you assumed, which is not reflexivity, is particularly non-generic, okay, because it has both its ends fixed, okay, and hence general arguments of path induction will somehow still work even in the presence of such things, because it's the path induction speaks only about generic things. So I don't know if this answers the question, but
yes. Yes, it answers completely. Thank you.
Okay. Okay, so going back, yes. So we have a notion of proposition, which you can think of seeing. Well, you can think of seeing this is, namely, that in your type there is no more information than the fact that it is inhabited or not, because as soon as you will, that's the intuition, and then we will have theorems later. As soon as no, okay, that's the intuition. So it's a proposition is about is a type for which you can only discuss whether it is inhabited or not, because this states essentially that it cannot have more than one inhabitant in some sense. So what matters is to have one, to have or not to have inhabitants, but there is no difference between inhabitants. Okay, contractible is a variation because it says that it is inhabited. It starts by saying that the type is inhabited, and then it says that everything is equal to this inhabitant. Okay, and we will see, well, in a while, we will see that contractible types are, of course, propositions. That's very intuitive, okay, because this is something that can be inhabited or not inhabited, while a contractible type is essentially, intuitively, a proposition which is moreover inhabited, and that we will have a theorem seeing that later on. So there's a little bit of vocabulary here, namely that this first component in the type is called the center. Okay, and the second component is the proof that it is a center. Okay, so I made a picture last time. I don't want to reproduce it here, but this picture, I do it in the ephemerus way. So this is my type, this is my center, okay, and this is any point, and you can contract this point by a path to this center. But a remark is that this notion of center is a bit exaggerated, because actually any inhabitant of the contractible type can play the role of the center. Okay. We will also discuss that a little bit later. So but you choose one and you call it the center. That's the idea. Okay. So here is an example, and since it is an exercise in the slides, I will not give the proof. I recommend to you not to look at the proof, okay, and to try to do the proof by yourself. Okay, so what is this type? It's a type of a pair of so it's for any type for SS. Yeah, I don't know how to remove this proof. No, well, ignore the proof. So it's a type from A is an arbitrary type, and then this type has as inhabitants a pair of an element of capital A and a proof that A is equal to X. Okay, and the theorem says that this type is contractible. So if you want an intuition, well, maybe set theoretically, you can think of this as the set of all elements of A which are equal to X. Okay, but there is just one. Sorry, all the elements of A which are equal to A, because you have fixed A. Okay, but set theoretically, you just have one. Okay, so it's a singleton, and contractible is being a singleton. So this is a very very sketchy intuition. Okay, and we will use this fact later on, but for the moment, I don't want to prove it, just to make sure that you try something by yourself. Okay, so now a few remarks about equivalence and logical equivalence. So here we have a statement, which is a very easy statement, but it's important. If you know that P and Q are propositions, then for them being logically equivalent is the same thing as being equivalent. Okay, so coming back to our Q-inv versus bi-inv problem, the fact is that bi-inv is a proposition and Q-inv is not a proposition. So I cannot apply the proposition in this case. But if we know that two types are propositions, and if we know that they are logically equivalent, then they are equivalent. Of course, the converse is trivially true. If you have an equivalence, you have a logical equivalence because there is more information in an equivalence. Okay, so how do we prove this? It's very obvious, but let's do it explicitly. So if you know that P and Q are logically equivalent, then you have a function f and a function g from P to Q and from Q to P. And what is left is to prove that you have a homotopy relating G composed with F with the identity. So we have to prove G of f of X equals to X for all X. But because P is a proposition, this holds for free. Okay, and same thing the other way around. So because P and Q do not have any structure inside, the second part of equivalence holds trivially. That's the idea. Okay, so this is important because we will make use of it. Okay, so now in the next well, like 10 minutes, and then a bit more than 10 minutes, and then after the break we will study a lot the properties of propositions, of contractible sets, and of sets, and then more generally of something called n-types, or types of a certain H level. Okay, so let me see in which order I'm doing that. Maybe before the break, I want to introduce this notion. So I will go briefly, without giving the detail, through what I want to prove, so that I have enough time to introduce you to this notion of H level before the break. So I'm listing things that I want to prove. First thing, I want to prove that all the type formers that we have seen, sigma types, pi types, plus, product, preserve propositions. That means, for example, if we know that each bx is a proposition, then for all x, a bx is a proposition. And by the way, we don't even need to know that A is a proposition. So it's even stronger than being closed under type formers, because A can be arbitrary. So let me state it again. If A is arbitrary, then pi x and all bx are propositions, then px bx is a proposition. Okay, so we will see why. And then a short discussion of Curry-Howard. So this you probably heard this association of names. This was very, very popular in the 90s and early 2000s. And what Curry-Howard tells is that types are propositions and propositions are types. And what we learn from homotopy type theory is that only half of this statement is true. So not all types are propositions. Some types are propositions, and we have a technical definition of what a proposition is. And then all the type formers that we have seen, because propositions are closed under these type formers, can be interpreted. So when we build complex types by making sure that every time we have propositions, okay, so we remain inside propositions, then we can read this correspondence as a real correspondence between types and propositions. But there is much more in type theory than propositions. That's the idea. So let me briefly go through that. And so you can read the product as the conjunction. You can read the function type as the implication. You can read the plus type as the conjunction. And you can read the pi and the sigma type as existential and universal quantification. And you can also read identity type as the equality predicate. Okay. Now let me introduce, and I think I will make the break after that. I want to introduce a whole hierarchy of types, starting with propositions. The next step is sets. So what is a set? A set is a type for which the following type is inhabited. So it means that you have that for all x and y in A, you have a proof that x equals A is x equal y in A is a proposition. Okay, so if I write it completely by expanding the definition of prop, the type asserting that A is a set is this type here. It shows that for x, if you pick an x, a y, if you pick a p and q that are proofs that x is equal to y, then p will always be equal to q. So what is the idea here? Well, the idea is that in this type, you will have inhabitants, maybe known, but you may have inhabitants, and then you may also have paths between inhabitants. But they are all equal. So there is no interesting structure between points of A, because all the paths between them, if they exist, must be equal. Okay. And this corresponds to the idea of a set, because in a set you have elements, okay, but you don't have anything between the elements. Now let's continue. Let's define what is called the groupoid, okay, in category theory. So it is a type Pxy is set of x equals y. So what it says is that this type has elements, and that the set of paths between any, no, sorry, that the type of paths between any two elements is a set. So in particular, you may have between two, maybe I write it with, you have your X, you have a Y, and here you may have a whole set of paths between X and Y. So in category theory, you call them morphisms. Okay, it's a groupoid because here paths are invertible. So it's a category in which all morphisms are invertible. But you don't have anything interesting like homotopies or things like that. You just have the notion of category. So now, next step. Suppose we want to write the type 2 type. Yes. So let me risk it. So I will call this 2 type, or I could call it 2 groupoid. Okay. Okay. 2 groupoid. It is a type pi x y of A is groupoid. Okay, so it is groupoid of A is groupoid of x equals a y. And then you see that this type allows me, it tells me that it has elements, and that between any two elements, if I fix two elements, what I have is a groupoid. What I have is a groupoid, which means that it has elements and it has morphisms between elements. So you have to think now that these one-dimensional things are elements. These two-dimensional things are morphisms or paths in this groupoid. So I hope you get the idea that if we continue in this way, so if we say that you start with something called the -1 type, which by definition is prop of A, so that was my starting point here. If I take this as a starting point, and then if I recursively define being an n+1 type is the same thing, is by definition the type pi xy, x, the equality type is an n type, you see that progressively I'm building a hierarchy of types that have richer and richer homotopical structure. Okay, that's the idea. Okay, and maybe I will anticipate now with the fact. So before that, let me explain you why I have a -1 here. Because, well, ordinary set theory and category theory start at dimension 0. So when you speak of a space, okay, you have points and they have dimension 0. And then you have paths, they have dimension 1, and then you have homotopies, they have dimension 2. And somehow a set speaks only of points, doesn't speak about paths. So in a set, you just have points. So set is a 0-dimensional thing. Then a groupoid speaks about sets and paths. So it has dimension up to 1. And then a 2 groupoid has dimension up to 2. So that's why in this hierarchy, we want is set to have dimension 0. And hence, because is set is generated from is prop by this induction, it is natural to call is prop the -1 type. And before the break, let me give you an interesting appetizer for after the break, namely the fact that, where is it? Yes, okay. So we shall show that isprop itself, which is level -1, can be obtained in the same form from a more primitive type, which we already know, which is iscontre. So we shall show after the break, okay, that the type isprop is equivalent to this type. Because of this, it is very natural to call this level -2. And in fact, the whole hierarchy which I discussed should start in the end from -2, which is iscontre. And I think we can make the break now and resume in 10 minutes from now.
Okay, Pierre-Louis, maybe you would like to stop sharing so that we can interact between each other. Or at least
okay, stop sharing. That's easy.
Sorry for speaking before.
That's easy, but I need to go to the right place. I need to go to Zoom and then to where j'ai compris, yes, and here j'ai compris, and here arrêter. Yes, yes.
Okay, so we can either close this session and start another one 10 minutes from now, or we can stay all day here. I don't know what you prefer, Pierre-Louis.
I think we can stay here. You will not see me because I'm going to just circulate in my home, but but no,
Okay.
it's the most easy thing to do. just to keep it like this. Okay.
Okay, fine. Well,